Welcome back to Linear Circuits. This is Dr. Ferry. This lesson is on equivalent resistance. The objective is to simplify a combination of resistors by replacing them with an equivalent resistor. For example, look at this case right here. It's kind of a messy circuit, and I'd like to be able to simplify it, and it'd be so much easier to work with a single resistor here. This lesson builds upon the concepts we've covered before. That is, resistors in series, where I can replace a series set of resistors with one resistor with this formula, or resistors in parallel where the formula for the equivalent resistance is right here. Let's look at this example. The way to approach something like this is to first recognize resistors in series or resistors in parallel and to replace them with their equivalent resistance. Now, people looking at something like this, a common mistake that they make is to think that these two resistors are in series with one another. They're not. In order to be in series, you have to have the same current flow through them. But the problem is the current flowing this way, part of it could go this way and part of it this way, so it's not the same current. So they are not in series with one another. However, these two are in series with one another because the same current has to flow through both of them. So I can take these two and I'm going to redraw the circuit with that simplification. And that's what I usually do on here. I draw a sequence of circuits. Each time I simplify it, I redraw the circuit. So that's 20, and this is the sum of the two is 20, and this is 30. So now it's much clearer because I've redrawn it that these two are in parallel with one another. So then if I redraw that one, I use two resistors that are in parallel. In fact, these are the same, and whenever they're the same, the equivalent is going to be half of that, and then that's 30. And now I've got two resistors that are in series with one another, right there, and I get 40. So the equivalent resistance for this whole system, this whole set of resistors, is just 40 ohms. Let's do another example. In this particular case, I've got these resistors are in parallel. I know because they share a node here and here. And so this is R1 in parallel with R2. And here I'm using the notation R1 in parallel with R2 to mean that it has a relationship, in fact that there's two of them, that it's a product over the sum. So over here, these are also in parallel because they share the nodes at both ends. So that is R3 in parallel with R4. And in this case, I've got a resistor in parallel with a short circuit. So that is 0 ohms. So then this combination is in series with this combination. I have R1 in parallel with R2 plus R3 in parallel with R4. And the order of precedence is this right here. I do the parallel first and then the series. Now let's look at a different example, this one here. We want to reduce this down to one resistor. It looks a little bit more complicated than the last one, but actually it's not. It's actually the same circuit as the example that we just did. I've just redrawn the physical layout of it. And that's something that for people to realize when we talk about resistors in parallel. You see this right here. It is actually in parallel with this, although physically it doesn't look it. But electrically it is in parallel because they are connected by nodes at both ends. So I could redraw this as R4 in parallel with R5 like this. And similarly, these two in parallel, and then that combination, this combination of resistors is connected to this combination through only this particular node. So I can redraw it this way. So the one thing that we might be able to do, or if you get used to this, is to redraw the circuit into something that looks a little bit more familiar to you. And also to recognize that electrically parallel is different than saying physically parallel. Now I've got a quiz for you. I'd like for you to find the equivalent resistance between this node A and this node C. Before we were doing between A and B. Now I want you to go between A and C. The solution here, we've got R1 and R2 that are in parallel with one another. And then across here, And all the current is either going to flow through R2 to get to R6 or R1 to get to R6. None of it's going to go in this direction because all of it's going to want to go this way. Current follows the path of least resistance. So this right here essentially short circuits all of this part of the circuit. So what we're left with is a series combination of R1 in parallel with R2 and that in series with R6 as our equivalent resistance. So to summarize, when we want to reduce a circuit that is fairly complicated, we look for parallel or series combinations and we replace each one with their equivalent resistance. And what I tend to do is to redraw the circuit every time I reduce something, and then I reduce it again. Every time I redraw it, then it becomes a little bit more clear other combinations of parallel or series resistance. And I keep following that path until I get down to one resistor. All right, thank you.